Okay, so today we're going to jump into random variables, so a slight change of topic, and I'll give some context to why we're doing that in a moment. All right, so focus on random variables today. We're going to talk through some of the tools for working with random variables, and we're going to need that for a reason. And to get to that reason, I want to do a little bit of a recap. So from the last lecture, we started looking at this idea of regularization as a tool to manage the process of overfitting, and we talked about cross-validation. So I wanted to try to put one slide that summarizes kind of everything we built up at this point when we think about modeling. So we spent a lot of time thinking about the loss function, and this is how we make sure that our model, which is determined by our parameters theta, fit our data. We saw L2 loss, we saw variations of absolute loss, and we'll see more as the semester continues. In the last lecture, we introduced a new idea of a regularizer. This is another term in our objective. We're trying to minimize our loss plus our regularizer. The regularizer is a function just of our model, our parameters. It knows nothing about the data. And it's there to ensure that our model is not too complicated. It's there to ensure maybe that we don't use too many features. And then we also introduced this idea of a regularization hyperparameter. This is this lambda, this thing we tune to set how much our model tries to fit the data versus tries to keep the model not too complicated. And we said that we would tune this parameter, this hyperparameter, using something called cross-validation. So we take a bit of our data, of our training data, hold off a little bit of it, fit our model with this loss, and then come back and evaluate how well it performed. And if it's not fitting our held out data, but fitting our data really well, then we're probably overfitting to our data, and we didn't generalize this held out piece of data. So that was cross-validation. And we'll tune lambda so that it fits both the data we have and the data that we didn't train on, that little held out piece of validation data. For the regularizer, we've already introduced two forms of regularization. They're actually pretty sophisticated. The first was this L1 regularization, this square, and that was trying to make our model sparser by zeroing out features. Okay. The other type of regularization, I should say the first one, was called lasso. So this was the first sparsifying regularization. The second kind of regularization we talked about was with this L2 penalty, taking the square of all of our model parameters. Okay. This is sometimes called ridge regression or ridge regularization. And this is trying to encourage robustness. Why does it do that? Well, it says don't put too much weight on one feature. Spread it out. Because if you put too much weight on one feature, you pay this quadratic penalty. So it's better to spread your weight across your features. Okay. We talked about how to tune these, how to manage this process of overfitting. Underlying this whole concept was this idea that we want our model to fit our data to not be biased towards, in this case of regularization here, we're biasing our model towards 0. If we crank this regularization parameter up really large, it says, you know what the best model is? The all zeros model. Always predicts 0. It'll be consistent, no variability whatsoever. Every time you fit any kind of data set, you get all zeros, right? But it's very biased. It doesn't really explain my data. So there's bias. And then there's variance. If I set this regularization parameter to 0, a model fits exactly the data it was given. You get a different piece of data, it fits a very different model for that different piece of data. That was variance. And we're trying to balance these two things. So we have this plot. I actually made this plot when I first started teaching this class. It survived. Model complexity, for some notion of complexity, how many features we use. Later in life, it might mean how many layers of your neural net. Complexity, as it increases, our ability to fit our data, the error we have on our data that we're fitting to goes down. Sophisticated model really fits my data, error goes down. But the variability in my model, variance, goes up. And so when I look at the validation error, the data that I didn't fit to, but I have it, I held it out, and I compare against that, I want to have good validation error, because that's a guess for what will happen if I take my model and bring it to the real world. I just held some data, I didn't look at it. Sort of, you're taking an exam, you hold some questions aside, some practice questions, you do a few practice exams, you go, okay, I think I'm ready for the real world, let's go check. You take out this, the questions you haven't looked at yet and go, did pretty well. Okay, let's go take the exam, right? We're trying to tune to the point on this validation set has the lowest error. So we take our validation data, we want to get the hyperparameters of our model, the complexity of our model, so we get the lowest validation error. And we hope that this is a good guess for how we'll do in the real world. Now, when I first started teaching this, I jumped into what I think is the most exciting lecture in the mathematics of this class, which is this deep statistical analysis of the fundamental bias and variance trade-off. And it occurred to me and the students after the lecture that they didn't have the basic concepts to understand this really cool statistical lecture. So we've since fixed that. And this is why we're going to talk about random variables and probability first, having those tools come back to do the analysis that is this bias-variance trade-off. The other plus side of this approach is you get to learn some more of the basic tools that will help you should you go off and do Stat 140. Or if you don't go off and do probability, you'll have at least some basic random variable knowledge you can use when analyzing complex probability settings. OK, so that's the plan. I realize I should take a quick pause here. Were there questions up to this point? Okay. No questions. I'll take it. OK, so probability. So our goal with probability is to try to understand, again, this relationship between the sample we have, the data that we fit our model to, and what will happen in the world. Right? And we're going to use these tools of probability to try to reason about those relationships between our sample and the world. We're going to have this idea of a population parameter. It's a weird idea, but we'll imagine that if we were to fit a model to the entire world, it's still a model. It's not going to predict everything correctly, but there is a set of parameters that I would have gotten if I just had everything, right? If I had, let's say my population is the entire class, if I took all of the students' grades in this class and tried to predict their final grade, there is some model that I could fit. It has some set of parameters. Those are the population parameters. But in practice, I only look at a sample of students. In this class, it's a bad example, I can look at all your grades, but let's say I'm in the discussion section, I can only see the students in my discussion section. Right? So now I have a sample. I'm going to fit a model on my sample. And I want to know how close is the model I get, the theta that I get, to the true theta that would have been fit had I fit the entire class. Does that make sense? So the source of randomness that we want to study is this sampling process. So I'm working with a sample. I'm fitting, I'm estimating parameters, things about my sample. And I want to know how they relate to what I would have gotten if I had built those parameters on my population. So the population parameter is a number describing something about the population. It could be something as simple as the mean, or it could be the linear model that I would have fit if I had the entire population. And sample statistic is the sample mean that I got, or the model that I fit. All right. We're going to focus on mean in this lecture. So in Data 8, you did a lot with the mean. Not all of you have taken Data 8. It's a requirement for this class, but some of the graduate students may not have taken it. What I've done here is we have links to the material in Data 8. If you've taken Data 8 and you've forgotten it, which I might have, you could go back and click on that link. Or if you haven't had a chance to take Data 8 yet and you're a graduate student, please take these links and try to review some of this material. All right. So we define the sample mean. In fact, all of Data 8 was focused on, here's your data, summarize your data. So we did a lot of our focus, almost all of our focus in Data 8 was on understanding the data we have, describing the data we have, and then sometimes drawing vague conclusions about what that means for the population. One of those conclusions that we introduced in Data 8 is the central limit theorem. And this is a big idea. We didn't prove it in Data 8, and we won't prove it here, but we'll derive parts of it. If you draw a large random sample with replacement, then regardless of the population distribution, the probability distribution of the sample mean, the mean you compute on your sample, will first be roughly normal for a big enough sample. It will be centered at the population mean, which is kind of cool. So the sample you get is probably going to be centered around the population mean. And if you do this repeatedly, you get a bunch of these different samples, and you get a bunch of different sample means, that the standard deviation of those means will decrease as a function of the square root of the population size. Okay. And it'll decrease the standard deviation of those means. We'll have this constant, which is the population standard deviation, which we don't typically have access to. But it gives an idea of how quickly we converge with our data. And we use this in Data 8 to think about how we might choose the right sample size. Okay, so today, we're going to try to understand some of these concepts using random variables and some of the kind of computations like expectation and variance on random variables. I have to say this. We are not going to cover all the material and probability that you should know to be a data scientist. I strongly encourage you to consider taking Stat 140. It's a great class, and it will cover a lot of what I'm going to say in much more detail. For those in CS, CS 70, and E, CS 126 also cover some of this material. All right, so first, what is a random variable? It's a confusing term, a random variable, because it's not a variable, it's a function. So a random variable is actually a function from the outcome of some random event to a number. Technically, it can be something more general, but we're going to say, for the purpose of this class, to a number. So to give you an example, take a fair coin. So a fair coin is a coin that allegedly would flip heads 50 and tails 50, or 50% each way. I can create a random variable x, which is 1 if the coin flips heads, that's the random event, and 0 if it lands tails. The domain is the input of my sample space. I could have heads or tails. And the range, the output, is 1 or 0. There's a notation that we will use sometimes in lecture to actually make it clear that this is a function. So a function from the actual sample itself to a number. We won't use this notation often. I won't go on this aside. There's a fun aside, it's kind of clickbaity. Coins aren't actually fair. You can flip, you can check out this physics study about how coins have a little bit of a bias depending on how you actually flip them. Coins fair, humans don't flip fairly. All right. So important notation. First, random variables are typically denoted with uppercase letters, just regular letters, X, Y, Z. And then regular variables, or values, numbers, are typically denoted with lowercase letters. A common source of confusion in this class is that we often work with matrices like big X, and we'll occasionally use capital letters to also denote matrices. I think we've in the past tried to use like double-lined X's to make it a little bit more clear that this is a matrix, but we'll do our best to try to make clear from now on we're not referring to a matrix or a random variable. All right, so let's take another example of a random variable. All right, suppose this is a population of data 100 students, that's what I'm studying. And then in that population, the students labeled in blue are data science majors. Okay? If I draw a sample of size 3, I could create a random variable for that sample, which is the number of data science majors in that sample. So the random event, the thing the source of randomness is the sampling of 3 people. So I get a set of 3 people, that's my S. My random variable is a function from that set of 3 people to the number of those that are data science majors. So you have a bunch of different outcomes, right? So I draw different samples, I get a different value for that random variable. This is why people think of it as a random variable. It's a variable that has a random value, but that's not really the right way to think about it. It doesn't have a value. It represents a mapping from a sample space to a particular number. So here we define the random variable y as the number of data science students in our sample. The input domain is all sample size 3 from the class, so a set of 3 individuals. And the range is 0, 1, 2, or 3. All right. The point of this lecture, and the reason we're going through all this for future lectures, is that we tend to use random variables in interesting mathematical expressions. And we want to reason about the expression itself by reasoning about the properties of those random variables. So I'll give you a simple example, maybe timely. So I sample 3 students at random from lecture. Let x1, x2, and x3 be the midterm grades for each of those students. So a function from the student to their midterm grade. I can create a new random variable y, right? Because it's an expression of random variables. And I might want to know what's this random variable y. It's essentially the average of the 3 students' grades. What's its distribution? What can I say about its properties? How does it depend on the distribution and properties of these students that I sampled from? And also critically, what is the distribution, which we should formalize now. But a lot of this work will be thinking about these kinds of functions, and I'll come back to this in the later half of this lecture when we start to use operators on random variables. Distribution, important concept. For any random variable, we need to be able to specify two things to define its distribution. One, what are the possible values that random variable can take? So its range. And two, the probability or the chance that the random variable will take each of those possible values. So each probability should be a real number between 0 and 1, inclusive. So it could be 0 or it could be 1. And the total of all possible probabilities should sum to 1. Really important axioms of a probability. All right. So assuming for now, and we're going to focus on this lecture on discrete random variables, so those that take on a finite set of values. I can write the probability that a random variable x takes the value x with this expression. That would be the probability that it, let's say x is 1 if it's the coin landed heads. So let's say probability x equals 1. And then if I can write it this way, if I write my probability function this way, then I should be able to say that for all the possible values that x can take, if I sum the probabilities, they should equal 1. It'll be common to work with a probability distribution table when thinking of these discrete values. So here we have one column, which is the possible values x can take, and the other column is the probability of each of those values. A distribution fully defines a random variable. So if I tell you the distribution, I tell you everything you need to know about that random variable. I tell you its values, and I tell you their probabilities. I can compute properties. So if I hand you a distribution, you can start to derive properties of that random variable, which we'll come to in a moment. You can also simulate from it. And this is actually a powerful tool that we introduced in Data 8. When I don't want to use the math that we'll teach you now, I can often take my random variable, sample from it, create data. If I create enough data, I can start to answer questions by using tools of data, mean, pandas, in Data 8, the data science library. I can compute plots, statistics on that data as a proxy for properties of that random variable. So simulation is a very powerful tool. Today I will try to cover some simulation in Python. In this class, I think we'll focus on NumPy's random library. But if you want to get more advanced, there's SciPy stats library. There's tons of tools for simulating from different kinds of distributions. And these can be really powerful, again, for trying to reason about complex properties of variables that would otherwise take more advanced calculations. There's often a point of confusion about random variables when we work with simulation. So if I take a coin and I flip it twice or 3 times, let's say, and it lands heads, heads, tails. It's a fair coin. What's the probability it lands heads? Okay, well, you might be going, it's a fair coin. I said a fair coin is probably 0.5 landing heads. That's an answer. That would be if I had a population probability distribution. It is, in fact, a fair coin. P is 0.5. But then I took a sample. I sampled it a few times. And I can compute a histogram here. And it's 2/3 heads, 1/3 tails. That's an empirical distribution. It's my observed distribution for that random variable. Right? In practice, when we make our empirical distributions big enough, we often treat them, it's more or less a proxy for the actual distribution. Often we may not actually know the actual distribution, so all we can measure is the empirical distribution. We'll, again, try to reason about the relationship between the empirical distribution and the actual true distribution of that variable, the population distribution. I bring this up because there's a fun example. If I flip the coin and it lands heads twice, what will it land the next time I flip it? Okay, well, who says if it lands heads twice, what's the probability it will land heads according to the empirical distribution? So empirical distribution is what I observe. I flipped it twice, it landed twice heads, and it landed 0 tails. So 2 out of 2, it was heads, and 0 out of 2, it was tails. So probability of heads is 1, probability of tails is 0 for that empirical distribution. Who wants to bet on that, right? Flip a coin. Would you take that bet? Yeah, so this is a challenge when we think about probabilities. We have small samples. It's not clear if we can treat those distributions or if we should treat those distributions as a good proxy for our larger distribution. And in fact, if you go into more advanced statistics, there's ways to deal with these kinds of scenarios using things like priors or ways to incorporate other knowledge. That is out of scope for this class. I just want you to understand the concept of empirical distribution and that these are good as I have lots of samples, but maybe not as good if I have really small samples. Okay, questions at this point? Okay. All right. Again, things you've seen in the past. We've done visualizations of distributions. We built histograms. We built KDE plots. Histograms give us a way to look at probabilities for discrete variables. KDE plots are continuous variables, have these continuous distributions. Important point here. So if I want to compute a probability of a range of values, I look at the area under the curve. So if I'm between 7 and 9, what's the probability that x for this probability distribution will be between 7 and 9? I take the sum of these red bars. If y is this continuous variable, it's the sum of the area under this curve. Important caveat, continuous distributions are weird. The height of this thing isn't a probability, it's a density, right? So if these are discrete, it's possible these things could be greater than 1, this density function. So you can't actually ask what's the probability that y equals 7.5. It's 0. You don't have an answer to that. It has to be a range of values, okay, for continuous distributions. For discrete distributions, I can go, yeah, what's the probability of 7? It's the area under this bar. If this bar has width 1, which they usually do for basic histograms, that's the height of the bar. Gives me probability. But you should check, is it the width 1? Because if it's not, it's a density. You're only lucky to call it a probability when it's width 1. Okay, questions? Moving right along. All right, so total area under the curve should be 1. And again, for continuous random variables, we have to look at a range of values. We can't look at a single value for that variable. All right, so quick practice. So here are some probability questions. Here is a probability table, and here's the distribution. Get this out of the way. So what is the probability that x equals 4? This should be pretty easy. Let's try it. So probably x equals 4. It's this bar, right? And I said this is the height of these bars, so these are width 1. So the height of these bars is the probability. It's 0.2. It's also up here at 0.2. So 0.2. Probably x is less than 6. But these are great exam questions, so it should be easy to answer these. Probably x is less than 6. Doesn't include 6, but it's the area under the curve to the left, so it's the area of this bar plus this bar, so 0.1 plus 0.2. 0.3. Probably that x is less than or equal to 6 includes the area of this bar, right? So it's 0.1, 0.2, plus the 6 bar is 0.5. Or sorry, 0.4. So 0.7. Probably x is 7 is 0. Jumped ahead. There's no bar at 7 equals, there's no bar at 7, so there's no probability of x equaling 7. Okay. All right. One more. So probability that x is less than or equal to 8 is the entire area of that curve. So that would be 1 for a probability. This should be pretty straightforward. These are pretty easy exam questions. So if you're confused about this, ask questions now or go to office hours. All right, so let's start talking about some interesting distributions, and we'll come back to analyzing these in a moment. So one of the first distributions that directly relates to flipping coins is called the Bernoulli distribution. So we write a distribution like this, so Bernoulli of P. Distributions have parameters, just like our models did. In fact, distributions are a kind of model. They model a probability function right here. P in the Bernoulli distribution is the probability of landing heads, or the random variable being 1. So Bernoulli distribution is a distribution over binary random variables taking on the value 0 and 1. So we have our probability table. So probability of outcome 1 is P. Probability of outcome 0 is 1 minus P. Important piece of notation, this little character here, this says x is distributed according to a Bernoulli distribution. So it's a way of saying the distribution of random variable is this distribution on the right. And we'll talk about some more named distributions in a moment. All right, here's a quick exercise. Suppose that x is a Bernoulli random variable with parameter p. What is the probability table for the distribution of y? Think about it for a moment. Okay. What are the values that y can take? Yeah. 1 and negative 1, right? So I have to be able to plug in all values of x. So x is 1, 2 times 1 is 2, minus 1 is 1. X is 0, 2 times 0 is 0, minus 1 is minus 1. Yeah, so those are the values. What about the probabilities? P and 1 minus p, they haven't changed. I'm just transforming the values of the random variable. Okay? So 1 and negative 1 and p and 1 minus p. Okay. All right, so Bernoulli, distribution of random variables that we just covered. We'll talk about binomial slightly later in lecture. There are other distributions that you've already seen, like a categorical distribution, which is a k-sided k-sided die, and it has a probability of each of the sides landing facing up. The uniform distribution, so distribution over the range over a finite, actually in this one, 0, 1 range. So uniform distribution over 0, 1. You can extend uniform distribution over an arbitrary range. And the normal distribution, which we'll talk more about later in lecture, actually in a later lecture. So these are two continuous distributions. Again, the important point is that each of these distributions has a parameter. They're a model of some probability table or a continuous probability function. All right, so this is the part of the lecture that we need to proceed to our bias variance analysis, and that is the definitions and the properties of expectations and variance. All right, so far, we've been thinking about random variables in their complete description. So we've looked at a distribution table which fully describes a random variable, or if we're sampling from a population, having all the possible samples in the population and their frequency fully determines our random variable. Or a histogram, again, a representation of that probability distribution. Now we're going to start to talk about more descriptive statistics or summaries of that random variable. Expectation, which is kind of the idea of the average but applied to the random variable, and variance, which is the idea of variance, the spread, but applied to the random variable. And these have really neat properties, and they'll allow us to do more interesting analyses with these random variables. And we'll see throughout the rest of this lecture that these things take our random variables. As I said earlier, when I build expressions of random variables, those expressions produce random variables. It's not entirely true. When I use expectation or variance, these are operators which will convert my expressions of random variables to numbers that I can directly reason about. All right, so we'll start with mean and variance. So we've seen these before in Data 8. So in the Data 8 textbook, we talked about mean as kind of the center of gravity of our distribution. So our expectation is going to compute the same concept. And variance is that spread of that distribution. Right, so let's start with expectation. So the expectation of a random variable x is the weighted average of the possible values of x, where the weights are the probabilities of those values. So there's two ways to write this. One is to say all possible outcomes that I could observe, for the probability of those outcomes, the value of x for that outcome. Okay? So all possible ways I could sample students, the probability of that way of that set of 3 students arriving, and then the function on that set of 3 students. We typically don't write probabilities this way, or expectations this way. We often use this form of the expression. This is saying for all possible outputs of the random variable, so for all possible, the full range of that random variable, what's the probability of seeing that value times that value? So to make that more concrete, if we take our 3 students sampled from class, this sum is a sum over 0, 1, 2, 3, 4. Right, so what are all the ways to get 0? What are all the ways to get 1, 2, 3, 4? All the ways to get 0 are captured in just one probability, one p. So p of x equals 0. All the ways to get 0 times 0. X equals 1. All the ways to get 1 data science student in my sample of 3 students times 1, and so on. Here, this sum is over all samples of size 3. Much bigger sum. All right. The bottom one is more common, simpler sums. We often have access to this probability function, so we can do this directly. Repeat this again. Expectation of a random variable is a number, not a variable. Is a generalization of the average. It gives us the center of gravity of that distribution function. And if we simulate a variable many times, and we'll come back to this, the long-run average of those simulations should converge to this expectation. So when we can't compute these expectations because the models are too complicated, we can often simulate and then take the average. Okay. All right, so let's try using this. Let's take a coin. So we have our random variable, x equals 1 if lands heads, 0 if tails. The expectation to compute it is we take, in this case, we'll sum over the outcomes, which are 0 and 1. So the first outcome here is 1. So the probability that we get 1 is 0.5 times the value 1. And the probability we get 0 is 0.5 times the value 0. So the expected value of x is 0.5. So what value, if I flip a coin, what value do I expect to see for that coin flip? 0.5. Do you expect to see x equals 0.5 ever? No. A little confusing. So x is either 1 or 0. But the expected value of x, what we expect to see is 0.5. Okay. So the expected value doesn't have to be a value in the range of that variable. It's the center of gravity, the center of mass of that probability function. So e of x is 0.5. This is not a possible value of x. It is the average. The expectation does not need to be a value in the range. Questions at this point? Keep going. All right, let's try something more interesting. So this is the variable we used earlier in lecture when we were calculating those probabilities. What is the expectation of this variable? So we have the probability function, so we can work it out just directly applying this equation, right? So the probability of seeing 3 is 0.1. Probability of seeing 4 is 0.2. Probability of seeing 6 is 0.4. And 8 is 0.3. Multiply these together, add them up. That is the expected value of this random variable. And again, it is not a value in the possible values that we could see for this random variable. Okay. So 5.9. We have a more interesting one. Okay, good. So I'm going to introduce variance, and I think we have some more interesting calculations in a moment. Variance is another one of these operators on a random variable that's going to take that random variable and map it to a number. It's defined as the expectation of the square of the difference between the random variable and its expected value. It's a pretty obvious, maybe natural notion of spread. So the difference is a good notion of spread, and then squared because these could be negative or positive. Right? So what is the expected square difference? This is the variance that we saw before, but now written in terms of expectations. Okay. The units of variance are in squared whatever x was, which is often hard to think about. So there's also the concept of the standard deviation, which is just the square root of the variance. It's another operator, just like variance, the standard deviation operator. Okay. So as before, variance and standard deviation return a number, not random variables. They describe the variability of that variable. We already defined it. One thing that's kind of neat is you can think of this variance as a notion of error, because it's the squared error between x and its expected value. You can sort of think of the expected value as a good guess for x. That's what you're predicting. And then x is its actual value. Variance is a notion of error in that sense. Variance is a notion of squared error. This is important because in the next lecture, we're going to use this definition to actually formally break down this bias-variance trade-off, and we're going to use this exact definition. Right? This is a general tool of probability. Who remembers Chebyshev's inequality? Raise your hand. That's impressive. Chebyshev's inequality is a concept we introduced in Data 8. I'll just jump to this link because it's worth seeing. If you hadn't seen it before, most people don't learn about Chebyshev's inequality until they're in their PhD studying statistics or AI. But we decided to teach it in our introductory class. It gives us a bound, a crazy bound, because it makes basically no assumptions. That says that one standard or two standard deviations will contain 75% of the mass. It's just true. It's a true statement. It's a pretty general statement, so often two standard deviations contains a lot more than 75%. But it'll at least have 75%. Right? So standard deviations and the cousin variance give us a description of the spread of our distribution. And if you go further, you say 4.5 standard deviations cover 95% of your data. Always. Probably a lot more, but always 95%. Okay. All right, so Chebyshev's inequality shows that these standard deviations are a good measure of the spread, or at least a good bound on the spread. There's another way to write the variance that's often used for analysis purposes. It's also easier to compute for exam purposes, so you should learn this formula as well. And that is, the variance is the expectation of the variable squared minus the expectation of the variable quantity squared. It's a little confusing. So this is the expectation of the squared x, and this is the square of the expectation. This is convenient because if I asked you on part A, what's the mean, or the expected value, you've just calculated that, and I go, now what's the variance? You go, okay, great. I just have to compute what? The expected value of x squared. How do I compute that? How do you compute the expected value of x squared? X squared is a new variable. So we just use our probability, our expectation calculation for x squared. So the values of x squared are, for all values of x, I take the square of it, and I take the probability that x takes that value. So if I give you a probability table, you just finished computing expectation, you can now compute variance very quickly. If you're a computer scientist, you might say, I can take one walk through my data computing both x squared and x at once, and then I can compute the variance. If I gave you this other equation, you'd go, well, first I need to compute the expectation, and then I have to walk again through my data to compute the difference squared to compute the variance. So 2 walks of your data, 1 walk of your data. So it's computationally easier, and it's great for exams. It's also worth noting this is kind of alludes to a neat property of our models. If our models have expectation 0, if our error is 0 in expectation, then we can just look at the square of the thing and not have to worry about this term when reasoning about variance. Go to this. All right, so here's a practice that we should go through. All right, so I have a die here that has 6 sides, and each side lands with equal probability. And I want to compute the expectation and variance of rolling that die. This is a very natural exam question. I think I have a Slido. Let's do it. Slido. Slido loads. There we go. All right, so what is the expectation of this die? What is the expected value? 35. I think you're missing a decimal somewhere. Does the biggest number mean it's the most likely thing? This is 35. Does everyone think it's 35? Is that what's going on? Or just doesn't show decimal points? Okay. All right. I think you guys are kind of getting it. Gonzalez, go for it. I like it. Okay. We only have, if I close this, they won't get to fill it out, right? Okay. Fill it out, people. Go quickly. Get your credit. Okay. While people are filling it out, there are questions at this point. Just a quick raise of hands. Is this familiar to you all? Okay. And for those who's not familiar, or I'm presenting it weirdly. Yeah, exactly. Okay, so some of this should not be familiar. It's great if some of this is. It will get less familiar as we go further. So bear with me. All right, I'm going to move to the next slide. Come on. And Zoom crowd, let me, if my voice is not loud enough, post a comment so we can try to adjust the audio. All right, we're going to keep going. All right, so to compute the expectation is relatively straightforward. I take the 1 times 1, 6, 2 times 1, 6, 3 times 1, 6, 4 times 1, 6, and so on. Or 1, 6 times 1 plus 2 plus 3 plus 4 plus 5. So 7 over 2, which I believe is 3.5. Right, so the 35, I'll assume that person, or the Slido thing, dropped the decimal point. All right, so that was the expectation. The more interesting one is the variance. So what is the variance? Okay. Oh no. Do I get the same Slido again? Okay, here we go. What is the variance? How do I calculate the variance of this die? So you might want to use that computational formula. So remember, the computational formula is the expectation of x squared minus the square of the expectation of x. Okay. Nailed it. Okay. As you're getting it. So it doesn't allow you to do decimal points in Slido. That's weird. You did see the answer. Good point. Okay. All right. Please fill something in so we can move on. All right. Come on. Let's get to 300. Go, go, go. There's no way to leave this open? Okay. Okay. So we're going to make it so it's open so you can fill it in. So let's do the variance calculation. We can do it both ways. So one is to compute the expectation. So it's going to be 1/6 times each of the possible values for this difference between x. So x goes from 1 to 6. And its expectation squared. So 1 minus 7 over 2 squared, 2 minus 7 over 2 squared. This would get tedious on an exam, right? So we could do it this way, and we get 35 over 12. Or we can use a computational method, right? And so here all we need to do is figure out what is the expectation of the variable x squared, which I believe is 91 over 6. I didn't calculate this through. Yeah, you can do the math yourself. 91 over 6 minus 7, so this is the expectation of x squared, minus the square of the expectation, which we already computed before, 7 over 2. So we get 35 over 12. Questions? All right, let's keep going. All right, so I said earlier that we would operate on functions of random variables. In fact, I showed you a sum of random variables. Now let's dive into that a little bit more. So a function of random variable is also a random variable, again, with the exception of these special operators that convert random variables to numbers. If you create multiple random variables based on some sampling process, then the function of those random variables is also a random variable. Okay, so if I have x1, x2, xn, then the square of them is a random variable. The max of them is a random variable. The ith, the number that are greater than 10 is a random variable. Sum of the square differences between a random variable and a constant is a random variable. Just the sum is a random variable, so the average is a random variable. So all of these operations are random variables. This is why random variables are so neat, because I can start with very simple probabilities, coin flips, and I can build up really complex things. And then I can try to reason about those complex things using the tools we've just demonstrated. And when those fail, I can use simulation on those little random variables to simulate those big complex things. All right. So let's go through some of the important properties of expectations and variance that will be useful in doing these kinds of analyses. The first is that expectation is a linear operator. So if I have a, the constant a times the random variable x plus the constant b, then the expectation of that is a times the expectation of x plus b. Really important rule. Next rule is the expectation of the sum of two variables is the sum of their expectations. No assumptions. Okay. So nothing about independence. This is just true. Let's prove it. How do we prove it? Oh, I didn't build the proof in. That's a bummer. I meant to highlight it, I guess. Okay. So we can walk through the proof of this relationship. So here, I take the expectation of x and y. I'm going to use that other notation where I say all the possible outcomes from my random event. This will let me deal with things like independence when working through this example. So I have the random variables x and y. These are functions, so functions of the outcome, times the probability of that particular outcome, summed over all possible outcomes. I can take this probability, these functions, put the s on the inside. So this is the function xs and ys. So this is just moving that function operator over. Now I can distribute this probability inside of this summation. So I now have a sum of xs ps plus ys ps. This already starts to look like two expectations. I can take this sum, slide it through. So break this into two separate sums. So the sum over xs ps and the sum over ys ps. These are the definitions of the expectations of x and y. Got it? So no assumptions about my random variables. I can show linearity. And of course, the other proof for ax plus b is an even easier version of this proof. So you should try to do that perhaps on your own. OK. So we've shown that expectations are linear. We can take the sums of random variables as the sum of their expectations. Oops. One important point is if I have a function g of x, which is nonlinear, like x squared, for example, then it is not true that the expectation of g of x is equal to the g of the expectation of x. This expectation operator works on linear functions. I can slide the expectation through linear functions, not through nonlinear functions. And we saw this in data 8, and I think earlier in this class. So if I take the random variable x is -1 or 1, x squared, what is its expectation? X squared is always 1, so the expectation of that is 1. But the expectation of just x is 0, assuming it's a Bernoulli random variable, so it's either equally -1 and 1. So the expectation squared is 0, but the expectation of x squared is 1. Right? Questions? These are important identities. We'll use them to prove some exciting stuff. We'll get some practice. All right. Let's actually use it now. So I want to prove the computational definition of variance using these properties. So let's walk through this. This will hopefully demonstrate these properties thoroughly. Okay. So my pen has died, so I can't seem to write on my iPad, so I'm going to use the pointer for this today, unfortunately. All right, so the variance of x is defined in the original definition here. I'm going to use a little bit of a weird coloring notation, but I want to color things that are not random variables blue when they're inside of expectations. So this e of x is not a random variable. That's a number. It's a constant. Okay? That behaves like our b over here. All right, so the first thing we do in this expression here is we want to break out this square. So we're going to expand the square here. So we have x squared, that's a random variable, minus 2, that's a constant. Ex is a constant, times x, random variable, plus ex squared, that's also a constant. Okay? Now what property can I use? I can use this property 2, the sum of expectations. The expectation of the sum of random variables is the sum of their expectations. To take this expectation and break it down. So I have expectation of x squared minus the expectation of 2ex times x plus the expectation of ex squared. Now if I go to property 1, the expectations of constants, let's do it right here. The expectation of a constant is just the constant. So this is a constant. So the expectation of x squared is just the expectation of x squared. Got it? How about this one? This one's a little trickier. So this expectation, this thing here behaves like the a in this expression up here. So this is a, and so a is over here. So if I take this expectation, I get to slide these constants out, so they pop out over here, and I'm left with just the expectation of x, this piece right here. Okay? And this expectation here, can't do anything about it. So the expectation of x times the expectation of x is the expectation of x squared, right? So this is basic algebra. And so I now have 2 expectation of x squared plus 1 expectation of x squared, which leaves me just minus 1 expectation of x squared. So just algebra. I'm terrible at algebra, so I work out every single step. This is how you derive this equation from this equation using just the 2 properties we've learned in class. Questions? Keep going. All right, so variance is a little bit trickier because we've got that square inside of that expectation. So if I take the variance of ax plus b, the plus b doesn't matter because it's just shifting the distribution of x. Okay? It's not changing the spread. But the a is going to get squared. Right? So when I take the variance with respect to the ax plus b, the a pops out and becomes the square of a. So constants multiplied by a random variable becomes squares on the outside of that variance expression. And then naturally, if I take standard deviation, I apply the same logic. I'll take the square root. So I take a squared, take its square root, so it's just the absolute value of a. Oh, I decided to prove this. Okay, well, we can work through this too. It's a good exercise. All right, so the variance, I'll use a computational formula for variance. So the variance of ax plus b can be written as the ax plus b squared minus the expectation of ax plus b squared. Do I want to work through this? Let's just do it. So on the right side, I'll use the identity we've already used. So pull out the constant. So this is just that linearity of expectation. I'll expand the squares one step at a time. So I have each of these terms. This is just basic algebra at this point. On the left side, we'll expand the squares again. And by the way, this process of expanding squares is pretty standard for all the analysis we would do with these kinds of, when doing kind of the bias variance analysis in future lectures. So frequently expanding squares, just do it. So a squared x squared plus 2abx plus b squared, just basic algebra. Now we can start doing some linearity of expectation. So we take our expectation, slide it in, slide it across all the terms. So all of these things are constants except for the x's, right? B is a constant, so nothing but linearity of expectation at this point. Now we can start to see things canceling out. So this b is going to cancel out here. This 2abx ex squared cancels out with this one right here. What's left? So then we have left a squared e of x squared minus a squared, the square of e of the expectation of x, which is this term right here. And this is a squared times the variance. This is the definition of variance of x. So this gives you, again, this property that the variance of ax plus b is a squared times the variance of x. Okay. So these kinds of derivations, I do them because they're helpful to think about these properties. These properties are what we use to do interesting analysis with random variables analytically. They're also, again, useful exam questions, so worth practicing these. Okay. The other thing, unlike expectations, remember I said the sum of expectation, or the expectation of the sum is equal to the sum of the expectations. This is not true for variance. So the variance of the sum is equal to the sum of the variance plus the covariance of the terms. Okay. Plus 2 times the covariance. Okay. I'm not going to do the derivation for this. You can work through it. It is linked in the slides. So the covariance is the expected product of the variations. We saw something like this in data 8, which I'll come back to in a moment. Let's just look at the definition for a moment here. This is a lot like, in fact, if y equaled x, then I'd have back the variance of x, right? So I'd be saying x minus e of x times x minus e of x, which is just x minus e of x squared, which is the variance of x. So the covariance of x and x is just the variance of x. But the covariance of x and y is this notion of their joint spread. Okay. Covariance has a neat relationship to correlation, which you would have seen in data 8, and I believe there's a link to it as well. So we can write this right here, if you look at this expression. This is a definition of the correlation coefficient that we learned in data 8. These terms here are constants, so we can pop them out. We pop them out, we're left with this piece up here, which is just the covariance. So the covariance, the correlation is just the covariance of x and y divided by the standard deviation of x and y. Okay. And these are the notions of x and y in standard units. And again, in data 8, and I think there's a link, if not, I'll add it. The correlation is what gave us that first version of our linear model, the slope of the line. If I standardize my data, I look at the slope of the standardized data line, it is the correlation coefficient. So it allows us to model a linear relationship, and therefore the covariance itself is capturing this kind of linear relationship between x and y. All right, so if x and y are correlated, then knowing x tells us something about y. But the opposite is not true, so if x and y are uncorrelated, it just means that there's no linear relationship. It could mean that x tells us something about y, just not in the linear sense. In data 8, I think we use the example of a parabola where there's zero correlation between x and y. But knowing x tells you exactly where you are on that parabola. So x and y are independent, then they're guaranteed to be uncorrelated, and the covariance will be 0. That's an important property. So if I know that these are truly independent random variables, then I can say their correlation, or their covariance is 0. Okay. And again, the converse is not necessarily true. Yeah, so they could be uncorrelated, but they may not be independent. All right, so we've talked about independence. Another thing that's very important to know for this class is kind of various notions of independence and a few key pieces of terminology. So if we have two random variables, x and y, and x and y are equal, then we'd say x equals y. It means for every sample, for every outcome, if we plug that outcome into x and we plug it into y, we'd see the same values for x and y. All right. X and y are said to be identically distributed if they're drawn from the same distribution. Okay? They're not equal. They're different random variables, but they're drawn from the same distribution. They're equal in distribution. It's confusing, so just say again, they're drawn from the same distribution, but not equal in value. It is worth noting, if they're equal in value, then they are in fact identically distributed, but the converse does not apply. All right. The thing you most likely will hear in any data science setting is independent and identically distributed. It's so common we call it i.i.d. So our x and y are drawn i.i.d. You might hear something like, I sampled people from some population, i.i.d. So each thing I observed was independent, so I drew a completely separate sample each time, same sampling process, and the process was in fact the same, so they are identically distributed. This means that knowing the outcome of x does not influence your understanding of the outcome of y. And therefore, they're independent, which comes from the name, independent and identically distributed. More of this is covered in later classes, concept of independence. It can get tricky as we start to think about, yeah. I don't want to tell you why it gets tricky because it'll make this more confusing. So yeah, independence here, we're just going to say they're independent. Knowing something about x doesn't tell me anything about y. Okay. So a simple example of this would be if I'm flipping two independent die. I flip them, they're equally distributed. It's fair, equal side, 1/6 probability for each face. Then they're identically distributed. Then they would be i.i.d. Actually, I want to stop here for a second. We talked about sampling with replacement and without replacement. So if I'm sampling from some population with replacement, and I draw two samples, and I'm sampling from some population without replacement, and I draw two samples, are both of those i.i.d? Let's talk about with replacement. So I pull someone from the class. I go, what did you get on the midterm? Okay. Put them back, and I pull another person from the class. Say, what did you get from the midterm? So they're independent, because let's say I do this process in a proper way, so they're separate, completely separate draws. Are they identically distributed? More concrete, let's go over here. So I pull someone from the class, and I ask them, what did you do on the midterm? You stand over there. And I pull someone else from the class. The problem is that that second draw, this person can't be in it. I changed the class. Right? So when I don't put the person back, they're no longer i.i.d. So when we do this statistical analysis, we often try to frame things as i.i.d. That's why I say when we do the analysis, we'll assume we put the person back, because we don't want to change the distribution. Now, when the class is really big, the chance that I would have pulled that person again is pretty small. So for very, very large sample or very large populations, the difference between sampling without replacement and sampling with replacement is negligible, so we don't worry about it. But for smaller populations, for smaller things that I'm sampling from, that first sample, if I don't put that person back, I could change the distribution for the subsequent samples. And so I can't assume things are i.i.d, and then the tricks and analyses I would apply become far more complicated. Okay. And I'll show you in a moment where this would break down. All right, so let's look at two variables. I have x1 and x2. These are numbers on my roll of my die. We already calculated their variance and their expectations. I'm rolling two die, x1, x2. I'm going to find two variables, y equals 2x1, and z equals x1 plus x2. Okay? So these have different distributions. It's the sum of two independent i.i.d. variables. And this is just 2 times one of them. Okay? You could think of this as x1 plus x1 as well, right? So two dependent. All right. I want to do this. Yeah, so what is the expectation of this? We can use our earlier properties of expectation, 2 times expectation of 7 over 2, or just 7. What's the expectation of this? It's the sum of expectations, right? It's also 7. Okay. So same expectations. What about the variance? All right, so let's derive the variance. So the variance of the first one, we can derive this a couple ways. I'm going to use, you could look at the covariance, let's do this simply. So the variance of 2 times x1 is 4 times the variance of x1, which is 4 times 35 over 12, or roughly 11.67. Is this other one going to have a higher variance or lower variance? Who says higher? Who says lower? Lower. Lower. Okay, let's see. So to compute the variance here, I'm going to take the variance of x1 plus the variance of x2. I said they're independent, so the covariance goes to 0. So I don't need to consider this term. So I get the variance of 35 over 12 plus 35 over 12. So the variance of x1, x2. We had this up here. Gets 5.83. Why was that lower? Yeah. Mm-hmm. That's right. The probability is those tails went down and have more mass pulled into the middle, right? There's many more ways to get to the center, this distribution. See that? There's more ways to get 7, right? Makes sense? You can also see from the distribution which one has more spread. This one's pretty spread out. They both go to the same extremes, but here a lot more mass in the middle. Okay? All right. I think I have a simulation. It's posted in the code where you can actually work through this process where we actually simulate, I think, 8,000 draws from both these random variables. In the interest of time, I'm actually not going to go through the simulation, but I encourage you to take a look at it. I think in lab and in future assignments, you'll use some of the basic code. It's pretty basic, so definitely take a look at it, but I'm going to skip it for lecture. All right, so demo for distribution of sums. We compute these expectations. Now let's see how we calculate without simulating, which we already did, so we skip that. Okay, so I want to do a quick recap of where we are at this point. So we've defined expectation and variance. We gave one definition of expectation, 2 key definitions of variance that you should know. We showed you some important properties of expectations and of variance, which you should know. And then some more important properties about sums of variables, both their expectations and their variance. Any questions at this point before we start to generalize this stuff? Keep going. All right. Earlier I said we'd introduce some distributions. We already told you about the Bernoulli. We can do our analysis of the variance and expectations of a Bernoulli distribution. And we can do this by operating directly on that definition of the Bernoulli, which is p times 1 and 1 minus p times 0. So expectation is easy. What's maybe more interesting is the variance. So we can do this same calculation for the variance. We use the computational form. And we get the variance is p times 1 minus p. So think about that for a moment. That means that if my coin is really fair, so close to 0.5, it has the highest variance in its outcomes. If my coin is less fair, it's more 1 or more 0, it has the lowest variance. So the highest variability of this random variable is when p is at 0.5. It's worth noting this is also used as an indicator. I don't know if I said this earlier. So we'll often, when trying to calculate sums of things that could happen or fail, we'll introduce a Bernoulli and say this is a random variable that could be success of 1 and fail of 0. We're going to compute expectations of successes. So we take sums of those. And there's a particular form of that we care a lot about, which is the binomial distribution, which is essentially the sum of n independent Bernoulli trials. So I take n i.i.d. flips of a coin of a Bernoulli trial. I take their sum. I define that as y. Y is now binomially distributed. We're only going to cover 2 distributions in this class, but actually you can do things like take squares of things, and they also have named distributions. And in statistics, a lot of study was devoted to understanding these kinds of distributions and their properties. But we're going to just focus on a few basics. So binomial has the binomial distribution. So there's a nice closed form equation for calculating the probability. So n choose y times probability, sort of how many times, if I have 3 successes out of, let's say n trials, then I'd say, let's say it's 10 trials, 3 successes, so 10 choose 3 times the probability of a success to the 3 times 1 minus the probability of success to the 10 minus 3, so 7. We can write this as a sum of Bernoulli trials, as I said earlier. And we can use that to analyze the expectation. So the expectation of y is just the sum of the expectation of each of those trials, or if there are n trials, that is n times p, because we know the expectation of a single Bernoulli trial is p. Likewise with variance, we use the same kind of analysis. Here, all of the coin flips are independent, so all the pairwise covariance terms disappear, and we're left with just n times the variance of the individual Bernoulli trials. So p times 1 minus p. Okay. All right, 2 key distributions. I want to wrap up today's lecture by connecting from populations to samples, and then in Tuesday's lecture, we'll actually use this to analyze this bias-variance trade-off. All right. So we've talked today about probability functions over populations, and I want to answer questions about samples that we draw from population and how we can use the tools we just built to reason about the properties of these samples. All right. And we've been sampling uniformly at random with replacement, and by making it with replacement, we can start to treat these samples as i.i.d, and it'll, in a moment, make this analysis much simpler. All right, so if I had sampled n samples from some giant population uniformly at random with replacement, I would have n i.i.d samples from that distribution. I'm going to skip this slide. In the notebook, we demonstrate how to do this sampling process. You can think of this general idea of I have a huge data frame that the population I don't typically have access to. I'm building some sample with replacement of that data frame, and I want to reason about properties of that sample. So here, I'll use big N, I guess, to be the population, and little n to be the sample I've constructed. Okay. And these are i.i.d. Yeah, so I think the easiest one to analyze here is the sample mean. So let's use this as an example. So again, I have the population of all people. It does have a mean. It has an average. That is the thing that I wish I knew, but I don't know it. I get a sample of that thing, and I take the average of my sample. That average is a random variable. And now I want to use the tools of random variables to understand the relationship between that sample and the mean that I didn't get access to. Right, so that's population mean is that fixed mean for the population. And then I have this sample mean, which I computed using numpy.mean on the data that I have. All right, so to see this, the mean of my data, because my data is random, it's random because I sampled with replacement, is just the, we got a random variable name, so I'm taking the mean of the grade and of the midterm grade. So each student, student S has a midterm grade, xi of S is their corresponding grade. I want to compute the mean. I want to estimate the mean from the midterm by taking just my sample. When I do that, I take the average of these random variables for the, let's say, 10 people I sampled. That is a sum of random variables. That is this sum of random variables. We use x bar here to be the random variable denoting the mean of my sample. My sample mean. So we can use expectation, linear expectation, to compute what this is. And this is the cool part. So if I apply linearity of expectation, it is the sum of the expectations of xi. Now, I don't know the population mean. That's the population parameter mu. I don't know it. But the cool thing is, because these are drawn i.i.d, this mean, the mean I computed on my data over here, its expected value is the population mean. That's great, right? So the expected value of my sample mean is the population mean. This is called unbiased. This is an unbiased estimator. In expectation, it'll do the right thing. But is it a good estimator? Well, there's another thing we have to think about, the variance. How variable will this estimator be? We do the same kind of analysis. So we take the variance of this sample. First, the population, the variance of x, I have this 1 over n that I have to pop out, becomes 1 over n squared, times the variance of the sum. Their i.i.d, I really want this with replacement, right? So if their i.i.d, the covariance has disappeared, I don't have to worry about that. So I just take the sum of the variances. Again, I don't know sigma. That's a population variance, right? But I can say that the sum of the variances is n times sigma squared. I have 1 over n squared. So I get the variance is sigma squared over n. This is a key result from data 8. We just derived it using just a few identities. I can take something I've computed, this mean. I know that in expectation it's good. Great. I also know that it's going to get closer and closer. This variance is going to decrease as I increase n. Linearly. The variance decreases linearly as I get a bigger and bigger sample. But of course, there's this pesky sigma squared. I don't know what it is, but if there's a lot of variability in my population, I'm going to need a bigger sample, right? Now we could ask, does this variance of my sample estimate sigma squared? So the variance itself is another random variable that I can compute on my sample. So if I compute the equation for variance on my data, that gives me a number, right? If I calculate the variance, that number is a random variable. Does that match the variance of my population? I won't do that analysis here, but you might have seen this sample variance equation where you have this weird n-1 thing going on. That's ensuring that that variance actually has an expectation matches the variance of my population. Again, we won't cover that status code for this class, at least for this lecture. We just analyzed the mean of my sample, and again showed that the expectation matches the mean of the population, and that the variance decreases by 1 over n. Okay. Questions? This is big stuff. Okay. And then I think in data 8 we use the standard deviation. Unfortunately, the standard deviation in the right units decreases 1 over root n, but again, for large n, this can squash quickly. All right. The last thing that I won't prove is that this is also normally distributed by the central limit theorem. And that is, for very large n, these things will look kind of like a Gaussian. The distribution of this statistic will look like a Gaussian. So, and that means if I take lots and lots of samples with replacement, and I get lots and lots of x bars, and I plot the histogram of those x bars, that will look more and more like a Gaussian, like this bell curve. Okay. And this is true no matter what the population distribution is, as long as it's sufficiently large. Okay. So how large does it have to be? Well, that sort of depends on the shape of population distribution. If it's not regular, then you're going to need a really large sample. But if it's sufficiently large, there's a large enough n for which this will be a true statement, which is nice. Okay? We will cover Bootstrap hopefully in a week or so. It was also covered in data 8. It's a way of simulating from the sample we have to try to guess the distribution of that statistic for the population. Okay. You get the center and the spread determined by these two parameters. I think I have a redundant slide. Okay. All right. Build this out. I think I have a demo, but I think I'm going to skip it in the interest of time. Yeah, actually, so I already said this, but I want to just reiterate it once more. So the expectation of x is an unbiased estimator of the mean, which is x bar, the sample mean is an unbiased estimator of the population mean, and we showed that. And it has a spread that we already defined, which I'm going to jump over. This is a square root law from data 8. So we actually finished. These are the basic concepts you need. Actually, we'll go back to a more useful slide. These are the basic concepts you need for the next lecture. I might have gone fast through here. Go back one more slide. Yeah, so these are the concepts you need for the next lecture. If you were to review something, you should work through these. Maybe there are some proofs I didn't show. You could try to practice those proofs. In the next lecture, we're going to go a little faster and apply these rules to actually try to calculate the bias variance trade-off for a model that's estimated using the squared loss. And we're going to treat that model itself as a random variable and study its properties. Okay? That's it. I will see you all Tuesday.